Welcome to the 17th lecture in our course on quantum mechanics. Now, we've just finished, for now, our look at the phenomenon of quantum entanglement, culminating with a discussion of Bell's theorem. Bell showed that quantum mechanics and the observed behavior of the quantum world cannot be squared with any theory in which the world is governed by hidden variables that act locally. And that was an amazing result. But we're now going to turn our attention to another important part of quantum theory. We're going to talk about a new way of looking at the theory. It's a way that has proved to be terribly important in making detailed theories of elementary particles in the present day. And so it's always useful to find a new way of looking at something that you already understand, because sometimes it can show you the way ahead. By the 1940s, quantum mechanics was already invented. The mathematical ideas were very well developed. There were lots of new challenges and applications of it all the time. And then along came Richard Feynman. Now, in 1942, Richard Feynman is a doctoral student at Princeton under John Wheeler. We've already met John Wheeler in connection with the delayed choice version of the interferometer experiment. This is the start of World War II, and both Feynman and Wheeler and many other physicists would soon be joining the Manhattan Project to develop the atomic bomb. But meanwhile, Feynman is doing his doctoral research on quantum theory. Now, Feynman is a brilliant and original physicist. His physics work throughout his career is amazingly distinctive. It somehow expresses his own personality. You can understand how an artist or a writer could do that, but how could a mathematical physicist do that? Nevertheless, he's able to look at the world in a very distinctive way. And a lot of his physics have many of the characteristics of a good joke: simplicity, surprise, and a kind of screwball inevitability. And Feynman, I have to tell you, is the hero of a great many physicists. All right, so what's Feynman working on? What's his PhD thesis about? Basically, it's a new way of looking at quantum mechanics. Feynman starts with a deceptively simple question. He says, how does an electron get from point A to point B? Or, since quantum mechanics is not determinate, he says, what determines the probability that the electron will make the trip from point A to point B? Well, Schrödinger would have said the electron's quantum wave travels through space. Here's the equation describing the quantum wave. And the intensity of the quantum wave determines the probability of finding the particle there. So must we imagine that the electron somehow solves the Schrödinger wave equation to figure out where to go? That's a pretty smart electron. And Feynman said, no, it's much simpler than that. To calculate the probability of going from A to B, here's what you do. You write down all the possible ways, all of the possible trajectories, all the possible paths of going from A to B. There's one that goes straight, there's one that goes over here, there's one that goes and circles Saturn and then comes back. All of the paths, no matter how ridiculous, you write them all down, and you can assign an amplitude to each path according to a simple rule. And I'm going to skip the details of the rule, but there's a very simple rule for ascribing an amplitude to each path. And then Feynman says, you just add up all of the amplitudes. Add up the amplitude for this path and this path and this path to get the total amplitude, quantum mechanical amplitude, to go from A to B. Now notice that adding up these amplitudes may involve a lot of constructive and destructive interference. Now that you have the amplitude, what do? You use the Born rule. The probability of going from A to B is just the amplitude for going to A to B, absolute value squared. So for Feynman, the electron does not have to be smart at all. It doesn't have to solve any equations. It simply tries everything. And the amplitudes add up all together. Think about it. When we talked about what a classical particle was, we said that a classical particle had a definite trajectory through space. Feynman says a quantum particle not only doesn't have a definite trajectory, it tries all the trajectories. And this came to be called the sum over histories approach to quantum mechanics. How could a particle get from A to B? Well, tell every possible history of the particle that starts from here and goes to there, add up the amplitudes, find the probability. Now, this idea can be illustrated in the Mach-Zehnder interferometer, our old friend. I have it over here to remind us. There's a simple rule for calculating amplitudes as the photon wanders through the interferometer. When you encounter a half-silvered mirror, if you're transmitted, multiply your amplitude by s, our old friend s, our favorite number, the square root of 1/2. If you're transmitted by the mirror, multiply by s. If you're reflected from the unsilvered side, the top side, multiply your amplitude by s. If you're reflected from the bottom side, the silvered side, multiply your amplitude by minus s. Those are the rules. So our photon starts out over here in this upper beam, and if we want to see how it could go to the upper detector, there are actually two ways. The first way is that it's transmitted twice. It's transmitted by the first half-silvered mirror, and then comes around and is transmitted again at this mirror. And so you're transmitted twice, 2 factors of s, total amplitude for that is s squared. Or you might be reflected twice. It might be reflected at the first half-silvered mirror and reflected again at the second half-silvered mirror, both times from the unsilvered side, and so the total amplitude for that is s times s, s squared. The two ways to get to this detector. The total amplitude is s squared plus s squared, just 2 times s squared. S squared, of course, is 1/2, and so 2s squared is 1. The probability of getting to this detector is 1. Well, what about the other way? Well, let's see. I could either be transmitted and then reflected, or reflected and then transmitted. Let's suppose you consider this the reflected then transmitted. If I'm reflected here, I get a probability amplitude factor of s, because I'm reflected off the top part of the mirror, and I'm transmitted here, another factor of s, that's s squared. How about the other way? Well, I'm transmitted through the first one, but I'm reflected off the second one, and now I'm being reflected off the silvered side, so I multiply by minus s. S times minus s is minus s squared. I add up the amplitudes. There's s squared, there's minus s squared. They add up to 0. Total probability, 0. You can't get to this detector. And that's exactly what we saw in the interferometer. Now, we've actually simplified the discussion from what Feynman talked about, because we've assumed that the photons stay in the beam, but Feynman would be happy to consider the possibility that the photon wanders all over the place, and he's actually able to figure out how to analyze that. Feynman figures out mathematical ways to include all possible paths, including weird ones that do quite bizarre and unreasonable things. In fact, Feynman is actually able to derive the Schrödinger wave equation from his theory as a kind of quick shortcut for figuring out how the amplitudes behave. So in fact, his idea, as strange as it sounds, is really quantum mechanics in different form. Okay, so what good is this? Well, it got him his PhD, that was very good, but it turns out it's even better. It turns out this idea leads somewhere. After the Second World War, in the late 1940s, Feynman's idea turns out to be extremely useful for working out the quantum interactions between electrons and light, something that had been pondered for 20 years by then. It turns out to be crucial for understanding quantum electrodynamics, or QED. Now, lots of people contribute to QED, Shinichiro Tominaga, Julian Schwinger, Freeman Dyson, but Feynman's work is decisive, because Feynman provides not only tools for solving problems in QED, he also provides concepts for thinking about those problems, and providing concepts is a tremendous advantage in proposing a theory. It's not just mathematics, it's also meaning. So what's Feynman's approach to QED? Well, Feynman draws little cartoons to represent the possible histories for the electrons and the photons in the problem. And these little cartoons are called Feynman diagrams. So I'm going to show you how to draw Feynman diagrams for quantum electrodynamics. So in the diagrams, these diagrams are actually diagrams of both space and time points upward. So the future in the diagram is at the top, and the past is at the bottom. And as you go from the past to the future, you should read the diagram from bottom to top. Now, in the diagrams, you might have solid lines going up, and we'll put little arrows on them. Those solid lines going up represent electrons. And we also actually will sometimes have solid lines going down. What are those? Well, they represent positrons. Now, what are positrons? Positrons are the antiparticles of electrons, the antimatter counterpart of electrons. They have the same mass, the same spin, but they have opposite charge to electrons. And if you put a positron and an electron together, they'll annihilate in a flash of high energy radiation. So there are positrons in the world. They were discovered in 1930, and they're represented in quantum electrodynamics by lines that look just like electron lines, but they point from the future to the past. In other words, in quantum electrodynamics, a positron is, roughly speaking, an electron that's going back in time. Now, we probably should not take that phrase too literally, but that's the picture in quantum electrodynamics. And finally, in our Feynman diagrams, we need to represent photons, and we represent photons by little wavy lines. Those are our photons. Now, in a Feynman diagram, the particles are either real particles, that is to say, photons, real electrons, and so on. These are lines in the diagram that come out of the diagram. They either go into the diagram at the bottom, in which case they're particles that were around at the beginning of the process, or they come out of the diagram at the end. They're particles that are around at the end of the process. And real particles are the particles you can actually see. They're the particles that might be detected by an experimental apparatus. But in addition to the real particles, there are also virtual particles, virtual photons, virtual electrons. What are virtual particles? Well, virtual particles are lines in the diagram that begin and end in the diagram. These are lines that are never seen by the outside world. They're part of the process. They come and go as part of the process. They're called virtual particles. And finally, there's one more thing in the diagram. It's how do these lines meet up? And it turns out that there's just one kind of way for the lines to meet up. It's called a vertex. And a vertex is an event, it's a point in our diagram, where a photon is either created or destroyed by an electron or a positron. So you've got a solid line, and then there's a point on the solid line, and a photon either is going away from or coming into that solid, that point. That's a vertex. There's only one kind of way to put the lines together, and that's the way. Okay, what Feynman did is he found a mathematical rule. Each diagram, each little cartoon that you draw, represents a quantum amplitude for a process. And it turns out that more complex diagrams, ones with more vertices, make smaller contributions. Each vertex involves a mathematical factor that's considerably less than 1, and so if you have many vertices, that makes the factor very small. Okay, so let's see how this Feynman picture, this Feynman cartoon version of physics, describes the electrical repulsion between two electrons. Electrons are both negatively charged. The two electrons are negatively charged, and so they push against each other. They repel each other. The simplest diagram describing this process contains two electron lines coming in from the past, and then a virtual photon travels from one electron to the other with a vertex at each end, and then the electrons go out, perhaps with different energies and momenta. Okay, so the electrons come in, and a virtual photon is emitted by one and absorbed by the other, and then the particles go out. Of course, that raises a question. Where did the energy for this photon come from? A particle just sitting in space, one of these electrons just sitting in space, does not just emit a photon for no reason. An electron has no extra store of internal energy to use to emit a photon. An electron in an atom can emit a photon, but that's only because it jumps into a closer orbit in the nucleus. An electron just flying through space, it doesn't have any extra energy to emit a photon. Where does the energy for the photon come from? The mathematics gives an answer. I'm going to try to translate that answer into English. And my translation is going to be a little bit imperfect, but it's a usable answer, and it gives you pretty much the right picture. And the answer is, where does the energy come from for the virtual photon? Well, we borrowed it for a while. You see, energy is conserved. Yes, energy is neither created nor destroyed. That's a great principle of physics. But remember the time-energy uncertainty principle. Remember that we had delta E, the uncertainty of the energy of some process. The energy was not necessarily completely fixed. And we had delta T, the duration of that process, our uncertainty about exactly when the process takes place. Because of the time-energy uncertainty principle, we can only observe things if the product delta E and delta T is greater than or equal to h, Planck's constant. That's the criterion for being able to have a certain kind of knowledge about the process. So if the virtual photon carries an energy delta E and only exists for a time delta T, and the product of delta E and delta T are less than Planck's constant, then we would never actually see any breaking of the law of conservation of energy. It would be hidden by the time-energy uncertainty principle. See, the law of energy conservation is still obeyed in any experiment where we measure the energy, because any experiment where we measure the energy necessarily is restricted by the time-energy uncertainty principle. Meanwhile, virtual particles can come and go quickly using energy borrowed from the universe, the whole transaction taking place sort of beneath the uncertainty principle. It sounds dishonest, but it is a legitimate consequence of the time-energy uncertainty principle. And so as a result, the electric force between two charges is carried by an exchange of virtual photons. And we can draw a couple of conclusions. The electrons can exchange one or more virtual photons, and they can do that even over long distances. They can do that over a distance that would take a large delta T to exchange, provided that the delta E for the photon is small enough. And so that means that because they can exchange virtual particles over a very long range, the force is a long-range force. On the other hand, the electric force between the electrons is weaker at large distances when they're very widely separated, because only virtual photons of less energy and momentum can be exchanged at that long distance and still stay comfortably inside the time-energy uncertainty principle. Indeed, the electric force is long-range, but diminishes with distance. Okay, let's explain another phenomenon. Let's explain the phenomenon of Compton scattering. In Compton scattering, an electron and a photon bounce off each other. They exchange some energy and momentum, but otherwise it's like two billiard balls colliding. And this was first measured and described by Arthur Compton in 1923. It was a very important early illustration of wave-particle duality. Photons are so much like particles that they can actually have collisions with electrons. Okay, so how does QED describe Compton scattering? Well, there are several possible diagrams. There's several ways this could happen, and all of the diagrams make a contribution. So what diagrams are they? Well, all the diagrams have the same input. There's an electron and a photon coming into each diagram. And all of the diagrams have the same output. There's an electron and a photon leaving the diagram, but the internal stuff in the diagrams, those will be different. Now, the most important diagrams, the simplest diagrams for the phenomenon, those diagrams will have two vertices. And so let's take a look at the diagrams that have two vertices. First of all, you can have one where the electron and photon come along, and the electron absorbs the incoming photon. And then a little bit later, the electron emits an outgoing photon. Now wait a second, you might say. That new photon isn't the same one that we had before. But of course, all photons are identical. You can't tell if the one coming out is a different photon from the one that went in. You can't tell whether it got absorbed and recreated later on. Photons are all identical. So that's a diagram that makes sense. Here's another diagram. First, the electron emits an outgoing photon, then it absorbs the incoming photon. And you might say, well, that doesn't make sense. Why would it emit an outgoing photon before it absorbed the incoming photon? Well, it's because you can borrow energy for a short period of time. Everything that's happening inside the diagram is happening sort of underneath the time energy uncertainty principle. And so that can happen. And really what we see in nature is what goes in and what comes out. This diagram's weird, but it's consistent. See, the crucial fact is we do not see exactly how the process we're talking about takes place. And this is exactly why the different detailed histories that we're drawing in the diagrams all contribute to the quantum amplitude. It's just like the interferometer. We don't see which path the photon took. All paths contribute. We don't see exactly how the electron and the photon interact. Every story we tell about that makes a contribution. And afterwards, it's impossible to say exactly how the process took place. The process, the particular diagram, leaves no footprints behind to tell you exactly what really happened. Finally, here's the third, and for my money, the strangest diagram that contributes. The incoming photon may suddenly turn itself into an electron-positron pair. And then the positron part annihilates with the electron and produces an outgoing photon. And you might say, wait a second, this electron that's going out is not the same as of course, you can't tell whether it's a new electron or not. Electrons are all identical. It doesn't really matter. Notice that in between the two vertices, there's a virtual positron. A virtual positron. In fact, this pair creation annihilation vertex, this vertex where a photon turns itself into an electron and a positron together, or an electron and positron turn itself into a photon, that vertex is the same kind of vertex we've been drawing before. It's just sort of turned on its side in time. There's still only one kind of vertex. And in fact, if you think about it, this diagram is really just like the second kind of diagram we talked about, except that in between the two vertices, this electron happened to go backwards in time, acting like a proton or a positron. Now, all of these diagrams are important in calculating the probability of a Compton collision between an electron and a photon. And if you include all three of them and you do the math, you get approximately the right answer. And if you want to get a more precise answer, you must include more and more complicated diagrams. You must include diagrams that have 4 indices with lots of virtual photons and positrons and electrons in the diagram, or 6 indices, and there are a whole bunch of those, and you have to include them all, each one of which corresponds to a mathematical expression, and so on. To calculate the amplitude, you include more and more complicated diagrams until you get tired or you achieve the requisite accuracy, and then you can calculate the total amplitude, the total probability, and you'll get a better and better answer. And that's the general way that quantum electrodynamics works. This gets pretty strange. This gets really pretty strange, but in fact, it works beautifully. I mean, just consider an electron moving through space. Now, actually, that electron in quantum electrodynamics may emit and reabsorb virtual photons over and over again. It continuously emits and absorbs virtual photons. The charge is surrounded by a kind of a cloud of virtual photons. And this process, this continuing process, changes the observed properties of the electrons, like their mass and their electric charge. In fact, when you sit down and try to calculate those changes, this process can lead you to apparently infinite results. You say, oh, the mass must be infinite, or the charge must be infinite. And that sounds bad. But what Feynman and the rest figured out was that there's a not quite magical mathematical procedure, which is called renormalization. And in this mathematical procedure, the unpleasant infinities can be persuaded to cancel out, and you're left with only the finite answer. And if you think that seems pretty fishy, you're right, it is pretty fishy, but it works like anything. And it is based in part on a physical insight. And the insight is that we've never actually seen a naked electron. We never could. Any electron that exists is always clothed in a swarm of virtual photons being emitted and reabsorbed around it. Those are always present in around the electron. And so all the properties we've ever measured about the electron always already include the effects of the virtual photons. So if we wanted to say something like the electron mass or charge would be infinite without the virtual photons around it, that assertion is actually physically meaningless, because we can never have an electron without its retinue of virtual photons continually emitted or absorbed. Now, as an aside, in some experiments, particles get very close together. We can get two electrons very close together, a little bit inside their surrounding cloud of virtual photons. And at extremely short distances, the electron properties do appear to be slightly different, just as predicted by quantum electrodynamics. Okay, where does that leave us? Quantum electrodynamics is the most accurate physical theory ever developed. It predicts certain things like the magnetic properties of an electron to 1 part in a trillion, 1 part in 10 to the 12th power. That's like being able to predict the number of grains in a truckload of sand and getting it right to the nearest grain. And quantum electrodynamics is also the prototype for all modern theories of fundamental forces between particles. All the forces are carried by the exchange of virtual particles. So, for example, nuclear forces, the forces between nuclear particles like protons and neutrons, the particles that are exchanged there actually have mass. And because they have mass, this means that we must borrow a bigger amount of energy from the universe in order to make them. We have to borrow at least mc squared, as Einstein reminds us. And that means that those particles, those virtual particles, can only exist for a very short period of time and can only travel a very short distance. And that means that the nuclear forces, which are carried by massive particles, massive virtual particles, can only act over very short ranges, less than 1/100 trillionth of a meter, 10 to the minus 14th meters, the size of a nucleus, but peanuts compared to the size of an atom. So, to recap, Feynman introduced his sum over history's view of quantum mechanics. And the view is this: what you do is you think of all possible ways for something to happen, including quite ridiculous ways that it could happen, and you realize that every possible history contributes an amplitude. That all the amplitudes are added together, there's lots of interference that happens there, and the total probability is just the square of the magnitude of the total amplitude. This is the concept of quantum interference raised to a very high degree. Everything is just quantum interference. And Feynman always drew inspiration from the old two-slit experiment. He said that the two-slit experiment contained all the mysteries of quantum mechanics. And his view of quantum mechanics was just the two-slit experiment, constructive and destructive interference, raised to the highest degree. Now, applied to quantum electrodynamics, the Feynman idea leads to the most precise physical theory ever, a theory with some odd aspects. It tells us that there are virtual particles that can come and go so long as they stay beneath the radar of the time energy uncertainty principle, so long as the energy that they carry times their lifetime is less than Planck's constant. It also tells us that electric forces, for example, are carried by the exchange of these virtual particles, virtual photons. It tells us that electrons just moving through space are surrounded by swarms of virtual photons, virtual electron-positron pairs, all kinds of stuff happening around even one particle flying through space. So even when nothing is happening, a lot is happening, even though we cannot, even in principle, say exactly what. And all of it contributes to the total quantum amplitude and thus to the probability of a process taking place. There are some apparent infinities, that infinite mathematical results, but they can be canceled out by this kind of interesting voodoo of renormalization. And the net result is that all of the forces of between elementary particles have the same general picture. They all have to do with exchanging virtual particles. And if the particles that are exchanged have mass, the force is a short-range force only. It's a curious picture. It's a remarkable picture, but it is the modern picture of how things work. And this business about virtual photons is so strange that next time we're just going to forget all the real particles and only think about virtual particles. How are we supposed to think about empty space? Is it a simple void, or is it filled with virtual particles? Next time, the quantum vacuum. I'll see you then.